And I usually give that privilege to graduates too. You graduate, you should be an adult, you're moving on, and more in our community together. But yeah, we'll be a pretty relaxed, comfortable group in the evening. I will say, if you use my first name at school, some of your teachers are going to look at you funny. So, but glad to have you all here, and looking forward to have some fun with astronomy.
Very good. Thank you, everyone, joining. And hopefully, on this first session of the actual session of the OPIS3, this Tuesdays are focused on the radio astronomy. And although the radio astronomy compared to the visual astronomy is very new, I think less than 100 years old. But I think the discovery that made it on this topic was tremendous in the science and astronomy and cosmology itself. And that is very cool that 100 years ago, nobody thought that radio astronomy gonna be a very high-ranked and progressive way of the study of the stars and cosmos and astronomy. But right now we are. And always science is unexpected become very uh, norm, and that's very usual on any kind of science and astronomy as well on this sense. Okay, let me quickly review with all of you here. Kinal, Arav, Vetri, and Rowan. All of you have able access to the WebAssign and Skynet. Did you register both of them or no?
I think on
Vet-
the email, like with
Vet-
instructions how to
yeah,
register.
you're not able. Okay, then I will. I think I forgot. I will set up for you a link for you to go and get the information for setup for your account. I'm gonna make it after this meeting. Hopefully, don't forget I put my to-do list. Then you receive the instruction for the both Skynet and WebAssign to go through it. And by the next session, that either Thursday or next week, if you have a question, just email back to me, and we're gonna set up you quickly on that. And let me go over share the screen. Do you wanna, before going further, John, you wanna add some brief introduction on radio? Because I think you are more expert than me on this. I believe based on the very activity that you are doing on the Marvel Reach as well on the radio.
I have I'm enough to be dangerous, I think, a little bit. I did put a link on the side for radio astronomy. Jansky, it's a neat read. If you get bored on a weekend, you want to see what he's doing. There's a Wikipedia article, a lot of nice articles. But he really was the father, I believe, of radio astronomy. And a lot of this came from, we used radar, was used during World War II to detect planes and things like that. And they started to realize it was good for other stuff because when nothing was around, there was this noise they were picking up. And they noticed when they aimed it up when the sun went overhead, it changed. And if you aimed it at different parts of the sky, it changed too. So it's kind of amazing how Jansky and others were able to just make antennas and figure out that you can detect space. We can actually detect stuff. And this is before the domes. The early ones were much like dual dipole, like we've kind of worked with at school, but ones you might see is basically two antenna wires. And you can use those, and it directionally looks at the sky, and we can pick up stuff like the Milky Way and all that. So I'm looking forward to learning actually quite a few things through our lessons myself, try to work ahead of everybody. And I encourage you to do the same thing. You can always work ahead and look at things ahead of time. You don't have to wait for anything, and make it real. If there's anything you have any questions about that you're just interested in, that's what you want to ask. So don't make this a have to, make this definitely a want to as you go through it. And if a lot of us can help each other out, understand things very simply, that's what I'll try to do. And if you have good explanations or things that you figured out, the challenge is to explain it to everybody else in very simple terms so we could all come to an understanding also. So
Thank you, John.
yeah.
Let me share you first the beginning of the material that we
Okay.
had.
As the boss is getting set up, I did put a little chat. One thing I generally do is set up a set of windows, and I'll put this on the side, that I will open up like the lesson in Cengage and Skynet, and then I'll hit the Afterglow link. So as you're learning how to do these things, I like to have windows where all this is together. So whenever and I always keep them open on my computer, which I never turn off. So those always come up. So every time they're all together, and it makes it really quick.
First question, yeah, thank you. First question that we're gonna have, this is a typical web page of the Cengage for the WebAssign that you're gonna see Astro Astra 100L, looking up Astro and Marvin Reach. I wanna see any of you have able to open this one in your WebAssign. Is it except the Vetri that has to be set up, but the others, Kinal, Arav, and Rohan, do you have access to that? This
No,
page?
I don't believe I have access to the course yet. I have a Cengage account, but I'm missing the course.
Yeah, there is a UNC code that I sent it, I think originally on the email, I think last Thursday, I believe. I sent it UNC class codes that you can use it, those key codes to access. Right now, when I see it here, there's only 2 individuals registered on this one. And let me see the other courses, the classes. This one is only Arav registered, and the other one, the last course, they had Arav and Kinal registered. Therefore, when you register it, therefore you have access to that, probably have it. But Rohan, if you can use it, the UNC code that he had when you log in, and you have to go to the, let me go back again to login to show you, because this is important. Let me log out here. Here, when you start, let me go Google or whatever browser you have, to say WebAssign login, and you come here to that Cengage website, Flexible STEM Learning. Here, you come here and I have login, but assume I log out, it's gonna be similar to this page again. Let's see, I log out.
Okay, sir, I was able to find the code. Thank you.
Very good, very good. Therefore, that's the only things. Everybody need to come and pick the username and account. Then you go inside the set, and you see on the left side my courses. We have 3 courses. Originally, we set up 3 courses, but I think we're gonna use one of them as needed, because I think Cengage has a specific requirement for each of them. You have to pay $65, but we don't want to do that. We want to have 165 for all of them, Therefore, the reason is that we're going to use the one of them that most of you are going to identify that, because I didn't notice this is going to be the case. We have to pay 3 separate cases, but we don't need it, because, for example, if you go any of them, either of these 3 classes, you're going to have the same labs from lab 1 to lab 9 that we're going to go over on 3 courses that we have. Therefore, as long as you have one of them ready, I think good enough. And I'm gonna, let me see the one that we have for students. For example, this one, I identify that and send it back to you, and make sure that all of you assign it with that course, and we go forward with that. Any question?
I have a
Go
quick
ahead.
question. So
Go
for
ahead.
2 of the courses, we only have access to the labs from September 27th for one of them and November 8th for the second one.
Yeah.
But the one that is currently open right now, it says that the free trial for the WebAssign is expired, so I can't access the labs right now, and I'll only be able to access them on September 27th.
I
Okay,
have the
it
same
means that,
problem here.
sorry, one question. Is that, if I understand correctly or no, when you have access to free, but by the September 27, is that correct?
Yes.
Okay, September, that's the reason, because normally they put 1 week or 2 week free trial, and after that you have to pay it. But the one that is right now, you see the schedule, I can change it, the schedule as needed. Therefore, you don't have to worry about that. But let me, after this meeting, I'm gonna set up only one of the classes to be used for all the 3 courses that we have. Therefore, you only, after September 27, you're gonna use the one fee for the 65 to access all of them. Therefore, you don't need it to pay separately for each of them. You don't need it to have access for all of them. But the time that you see it here also, I'm gonna adjust it to make sure that all of you guys have access till December, end of the session for this semester.
Got it. Thank you.
Okay, you're welcome. Rowan, you had the same issue? Okay, that's gonna be solved, I think, based on that. Let me go over the first session. Let me stop sharing again, share it back again to make sure that I don't forget the sounding, because we have to make some video. Okay, here you will see the lab 7. Each lab gonna be similar to each other, but we're gonna have some intro. Normally, each lab has 3 sections: introduction, background, and procedure. And some of them has instruction also. For example, if we go back to lab 1, that's the first lab. Here you see we have introduction. In addition of the introduction, we have instruction here, background, procedure. Here we have 2 procedure on the lab 1, but on lab 7 we have only 1 procedure. Therefore, it's simpler and easier here. When you go each of them, for example, introduction on lab 7, you're gonna see a video page. For example, in here, lab 7. 2 video here. There is an enhanced video provided by an organization, we call it Glass Education, that they enhanced it, added some features helping you guys to review the course if needed. But most of them you don't need it to go to look through it. But for some of them, I will provide some basic videos to look over to see how it looks like. But we're gonna give you, John and I, introduce all the information that is needed. Enhanced video, as there is some features that you're gonna see it. I prefer to if you wanna use it enhanced version. We're gonna look through it. Most of them is few minutes, or maximum 10 or 12 minutes. It's very short. Let me go over one of them.
Welcome to Lab 7. In this lab, you'll use our 20-meter diameter radio telescope at Green Bank Observatory in West Virginia. It's 6 stories tall, 150 tons, and you'll move it around to collect spectra along the plane of our Milky Way galaxy. Radio astronomy is the other type of astronomy that you can do from the ground, and it's very different from visible light astronomy, which is what you've experienced so far in this lab course. For one, you can carry out observations during the day, even close to the sun, and you can observe through the clouds, even when it's raining. The radio sky is very different from the visible light sky, and you can use it to measure and do things you otherwise wouldn't be able to do. However, these telescopes are very expensive. Each one is custom built and maintained, and there are few of them. And consequently, most students and even many professionals simply don't have access to radio telescopes. But through Skynet and this lab, you do. Now, in this lab, you will use this telescope to measure the speeds at which matter orbits the center of our galaxy. You'll then use these measurements to determine something called a rotation curve. How fast is the matter orbiting the center of our galaxy as a function of its distance from the center? Using this rotation curve, you'll determine how the mass is distributed in our galaxy. Is it concentrated at the center, like in our solar system, or is it spread throughout the disk? You'll then measure how much mass is enclosed within different distances from the center. In other words, you'll weigh the galaxy. And you'll determine if the galaxy is composed primarily of visible matter or a combination of visible and dark matter. Lastly, there are no observations to put in for Lab 8, but in the equipment section of Lab 8, you'll find a short list of fairly common supplies that you'll need to round up before you can begin that lab. So I would start rounding up those supplies now. Okay, that's it for this video.
Okay, this lab, as you see it on this section, it just introduced the introduction for this one. It's basically what the Professor Dan provided as a kind of key item. I want to emphasize on that. We're going to focus on radio astronomy versus visual astronomy. That's the one key item. What's the main telescope that we're going to observe from that? You heard on the video? What was the radio observatory?
The Green Bank.
Very good. Yeah, Green Bank, that is located on West Virginia, about 20-meter wide. Is almost 20-meter wide. Is very large telescope, and this is rotating. And we're gonna see the picture as well. And therefore, what's the advantage of the radio astronomy versus visual? For example, when you go out to see the star or constellation on the sky, what's the difference between the specific feature of the radio astronomy versus visual astronomy that Professor Dan said on the video?
You can do it during the day and when it's cloudy and rainy.
Very good. Yeah. Therefore, that means that most of the time, the visual observer, when it is cloudy and kind of dark, is not on the daytime. On the daytime, we can only observe sun with a specific solar scope. On the night, if it is cloudy, we are done. We cannot do any observation through the clouds or rain or other things. But radio astronomy, it can be done almost 24/7. Also, if it is, we can observe the object near the sun as well, if it is cloudy or rainy, except a few times that is very heavy storm might be causing this radio observation difficult. Another key feature that Professor Dan doesn't mention here that is important, we don't have to have a very radio signal near the observation site. Because of that, radio Green Bank Observatory, they call it a dark radio area over there. If you go there, you may not able to use your cell phone. Because there is no signal is there, and very good opportunity if you have a chance to go there. Very good training sessions they have along the year, and that's going to be good future of the radio astronomy that has more opportunity to observe than the visual that versus the cloud and other rainy situation on the atmosphere. Any questions so far? Okay, let me share the.
I'm gonna share an image if I can real quick. Can I share something?
Go ahead. Go ahead.
Here's a neat another graphic I always think of when we talk about radio astronomy. Is what we're looking at here is what gets through and what does not get through as far as light and types of light. So the rainbow there shows you our visible light, and we can see pretty much, this comes through. So when we look at the sun or anything out in space, we can see red stars, green stars, blue stars, all types of different colored objects because the visible comes through. But anything beyond into the UV is blocked out quite nicely from by our clouds and our atmosphere. But then radio opens up again. So you go down in between this, before you get to radio, this is infrared. And some of this gets through also, and that gets us into, we can talk about greenhouse effects and all that. But if you go farther to the right, this radio, our atmosphere is transparent to that. So it's like somebody turned the dials and adjusted this so we can see what we want to see, the visible and the radio safely, and it also comes through nicely. It's different ways we can image space. For imaging anything in the infrared, you need to be on top of a mountaintop. You start to get past the clouds in the atmosphere or up in space. And the same way for anything in the ultraviolet, you need space-based telescopes. But for radio, we don't need that. We can just use simple ground-based telescopes.
Thank you, John. That's a very good timing and information that we're going to look over. Thank you. And as John mentioned, let me again stop sharing. I forgot to share the sound as well. Yeah. Here is a short video about the electromagnetic wave that is introduced the radio astronomy from NASA as well. We're gonna go look over to this short video as well.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
This was a short video that shows the basics of the benefit and learning that we have from electrowave, and also similar way that John provided. I sent some links on the chat that all of them give some information whenever you have a chance to look through it and identify. And as I mentioned, this one was either wavelengths is measured based on the nanometer. Nano is 10 to power of -9, and or angstrom 10 power of the -10 kind of meter compared to the other wavelengths. And these tools, if you have a time, you can look through it and learn more. And if you have a question, you can back to us. But the things that we're going to look through the lab 4 is we're going to lab 7. We're going to go to the background we're going to go to the information that we needed on this lab. As we mentioned, that measure of the speed, several things that is keyword on this lab that we're going to learn. We're going to look through our galaxy, Milky Way galaxy, and we're going to look through the radio wave measurement and see how our galaxy matter orbits inside the galaxy. This is a key item that we're going to learn on this lab, to how we can do with simple measurements through the radio telescope, Green Bank Observatory. We learn those. And then we go through how we're gonna use this information to get some more data on here. The only equipment that you needed here is your internet connection and computer. First topic that we're gonna learn is the Doppler effect. Anybody of you have studied Doppler effect on the physics or school yet, or no? Any question? Any answer? Do you learn Doppler effect before in your physics?
The Doppler effect, that's like the change in wavelength of a wave because an object is coming or going away, correct?
That's correct, exactly. And a similar way, normally on the middle school or high school, you will learn from the sound of the train that is approaching to the train station and going back. When the train comes to your side, when you're standing on the train station, it sounds differently from the way that the train goes away from you. And that shows the object is moving toward to you or away from you. That was applicable for both sound and both radio and also visual light as well.
Yeah, if you want, I can share a FET real quick.
Sure, go ahead.
Go ahead, illustrate this. A few different ways to do this. So let's see if I can share that. There we go. All right, so in this window, I have a light source, and what it shows you is the wavelength of the light coming out. So here's green light coming out, and we can see these bright areas being the crest of the wave as it travels away. So if I look at the far edge of here, it's hit. So those waves are coming across. And now I'm going to change the color to red, and you'll notice what happens is now that they're farther apart. So these are longer wavelengths. So red has longer wavelengths as we go through this. Now if I look their side, it's like hit. And if I go the other extreme, go to the purple, now they're very much closer together. So now we have hit. hit, very quick. And so when the lines come across, when the wavelengths approach us, or we cut across those lines, the rate at which we're seeing that's our frequency of the light, and the frequency determines the color. If it's very not very often, so they're very long, then we say they're very red. If they're very close, it means it's more blue. And like infrared is longer, and radio is very long. So if I don't know if you can you see my my cursor in there? Is that visible? Okay.
Yes, I can see it. Yeah.
All right, I'm going to change it to something like green in the middle, and I put my cursor here. So somebody standing still is going to see the lines blip, 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 blip. So here comes the frequency of the light coming in, and it's a nice even intervals. But if I take that person and I move them towards the source, we'll notice that the rate at which they hit is more often. So blip, 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 blip. And they go away, it's blip, blip, blip. So even though what we see from our view is green, when the person's moving away, they'd actually see red. And when they're moving towards, they could see blue. And the same way, if the source is moving and you're not moving, the same thing happens. So this is red shift and blue shift of objects. I think a lot of times we've heard red shifted objects, the idea that the universe is expanding out. And this is the Doppler effect. It's just that there's a color, but the color's changing because either the source is moving or the object moving, a little bit of both. And that sets up our effects. And I'm going to go see if I can share. I'm going to stop that one and try to share another one, which isn't too bad. Oh, I lost it. Let me see if I can change it over. There we go. I'm going to close that and try this again. All right. Let me see if this one shares. All right. Oh, here you go. So this is showing an object that's actually moving. So you can see on the front edge, going towards the front observer, the lines are more often, where the back observer, they're much farther apart. So who sees blue and who sees red? Any guesses out there? And I got my chat turned off. I can't see it. So
The front observer would see blue and the back would see red.
exactly.
Perfect.
And that's what we can use too for like the Milky Way moving. If you look at the radio waves coming off the Milky Way from one part to another, we're going to see we can actually catch the shift. We can actually measure how fast things are moving this way. And we can actually measure how fast stars are moving by looking at what their color should be and what it is, how much those have changed. We can get a velocity off that. So that's a big part of our lesson today.
Very good. Thank you. This was very good and also aligned with the things that graphically in here we're going to show on the lab. As you see it, and John also demonstrated, if there is a star here and we are moving by the spacecraft on different direction, either right and left, if the star is located constant without any moving, we're gonna see the crest of the light on any direction. This is 1, 2, 3, 4, and 5 on the center. There's a crest of the wavelength that is scattered all around the source of the light. And if the source is at rest, not moving, we're gonna see the same wavelengths on every direction, because those are the spherical and circular pattern all the way scattered around the source. But when the source is moving, for example, on the time 1 is here, time 2 is here, 3 and 4, the circles are going to be same, but the location of the circle is moving as John showed it. And here, if the spacecraft is also not moving, staying in one place on the right and left, here the astronaut on this spacecraft gonna see the light is shorter, shifted to the blue, and on this side, on the left side, see it shifted to the red, and the wavelength is longer. Therefore, this is a formula that normally we're using for the Doppler effect. You don't need to memorize this formula. That is just only show how it works. Lambda OBS is the wavelength of the wave that is observed by the individual or astronaut or device on a certain location. And this is lambda EM is the emission of the electromagnetic wave at the rest. And when we have a kind of wavelengths become shorter, like the one that is on here, it's going to be lambda EM minus delta lambda. And on the other side, that has become larger, it become lambda EM plus delta lambda. And delta lambda is a change of the wavelength due to the movement. And this movement is kind of relative to the object of the source and also observer. And we calculate it this way. It means that it is emission wavelength times the delta V divided by C. Delta V is the relative speed of the wavelengths object, either source and the observer, and C speed of the light. If, for example, this delta V is become close to the C, that's going to be very extensive. It means that those objects are moving totally with the speed of the light. But one thing also we have to consider, this line of the sight that we see it here, the movement is always in this picture happening along the side of the sight. But sometimes the object is not moving like direct to us. If the source is here and observer here, sometimes the movement is on different direction. For example, on this direction. Therefore, we only need to calculate the one on this formula that is along our side. It means that direct connection between the source and us. And we're going to learn how to measure this one. We don't need to memorize any formula or any concept like that. Only we're going to figure it out how this movement along the side from the source to the observer, it's going to impact our kind of measurement to the blue shift or red shift. If, for example, this star move it on this side, but part of it move it toward the observer and again create the blue shift, but less intense than the one that moving directly toward us or away from us. Any question on this Doppler effect? Hearing none. We go next part in here. This is a kind of, we call it the 21 centimeter emission line. As you see it on this picture before going forward, this is a picture of the or galaxy that is plane of the galaxy visible that is observed here. As you see it here, in some area we have black dark areas. Here is dark, here is dark, and there is a dark patches of the light. We see it on this picture of the galaxy. This is a picture of the galaxy on the visual light. And to measure the Doppler shift effect on the galaxy that is rotating around the center, we needed to use a specific consideration here. One of the key items that is helping us in here, this is a picture on visual light, and another picture you see it here in the radio wave. Although radio wave doesn't have a color, as I mentioned the last orientation session, on the visual light we have a color. We can identify by our eyes different colors like red, blue, and green, orange, and yellow. But the other waves like a gamma ray and the radio wave and the X-ray, we need to assign the color to identify which one is the more intense and which one less intense. Here, we are assigning the specific code of the color for the radio wave lengths that we're going to identify here. As you see it on the center, we have higher intensity. In some area, we have less intensity. You see some different colors, and those are assigned to identify each properties separately. But actually, radio wave doesn't have any color. This is kind of artificial, virtual color that we assign it to radio wave to see it. And what cause of the radio wave that we're looking? We call it 20 centimeter emission line. And what that emission line is that if we consider this is based on the hydrogen, cold hydrogen atom. Why we using called hydrogen atom? Because hydrogen atom is abundant in all universe. The one of the atoms, the basic atoms that is available on all entire universe and cosmos. And that's the reason we're using that. And that's the simplest one. We have one proton and one electron, one proton at the center, electron at the surrounding region. And when they are both of the proton and electron rotating in the same direction, as you see it, both of them rotating around the like a magnet on the north and south pole. It is rotating on the anti-clockwise. And if they are rotating on the reverse than each other, that create a 21 centimeter photon. That is, we call it this 21 centimeter emission line. That's the kind of lowest energy that we may have on the electron system that we have. And consider in here this kind of emission, because it has the lowest energy because of these changes. Normally, energy created when an electron comes from far distance on the lower orbit or goes to the upper level. But here, the electron location doesn't change much. The only changes happen in the orientation of the spin of the electron itself. And that's because of that create low energy, and low energy is related to the electromagnetic wave. As we mentioned here, and the video that John provided, when we have a lower energy, we have longer wavelengths like radio. When we have higher energy, we have shorter wavelengths like a gamma ray and X-ray that we're using on the medical devices that can penetrate through the small skin and show the internal body and organism. The things that we have it here, why we using this future? That's one main question, why it is like that. The reason is that based on this picture that you see it, we have a very large amount of the dust and molecules inside the galaxy between us and center. This is the center of the galaxy. But you see it, we have a dark region here that exists, and the radio wave is long enough, like one that you see it in here is very long. And normally this is basic things that you have. The wavelength is very large, and the dust cannot prevent a kind of radio telescope to reach us. Why it has happened? That's one of the basic you answered, because we can see it radio wave when it is cloudy. Although we cannot see the light visual, but we can see the radio, because radio can penetrate through the dust, can penetrate through the clouds. And that's the reason we're using this low wave frequency to measure the radio waves on the galaxy. The picture that we're seeing on here. Any question in here? The idea basic is that when the electron and proton is moving in the same direction, rotating around each other on the like a two magnet, they had one certain energy. When it is rotation is different, it creates a kind of lowest energy. We call it 21 centimeter emission line. That is basic of the radio astronomy observation.
Yeah, another way to think about this is like we've all ridden a bicycle, and the hardest part on a bicycle is just getting started, right? Trying to balance that bike, you just can't do it. Once that wheel starts turning, it's easy because that wheel doesn't want to change what it's doing. It wants to stay in that orientation. And so these electrons have a spin characteristic that we're talking about here, which is just so solid and fixed. But for some reason, once in a while, it flips. And that energy change corresponds to the wavelength, this 21 centimeter line, which corresponds to the energy of that flip, the wavelength of that flip. And so it doesn't ever happen, except, hydrogen, it does happen once in, millions, but there's so many particles. So if it happens once in like millions of years, but we're talking about something where we've got 11 million years. We got billions and trillions of particles, and it works. So actually, you could pick this line up from our sun itself. Our sun puts this off. And in like Jupiter, even we can pick this up in it with radio. It puts off a radio signal because the hydrogen has enough hydrogen that you're going to see a flip occasionally happen. It allows us to see the invisible. And the hydrogen, we believe, is distributed throughout the galaxy in a way that we can use it.
Yeah, exactly. As you mentioned, John, very good point on that. Although that event flip may happen many million years, but because we have abundant number of the hydrogen in the universe, we can able to detect this emission line easily for the or the devices that we have on the system. Then here, as you see it on this picture, we're going to look through a kind of geometry of the system that we're going to look through it here. As you see it on the center, this is the center of our galaxy that is located here. And if we look through a section through the galaxy, for example, our sun probably is located somewhere here. We're looking to the center of the galaxy. Center of the galaxy is located somewhere here, as highlighted by an arrow on this location. And then when we look through here, as you see it, everything is rotating around the center. Some of the items here rotating this way, and some of them on here rotating the other way. And none of them is rotate. This velocity that they may have is not exactly on this line of the sight. For example, if we have one object here, this object may move this direction, but there is no velocity along the side toward us. Although we have showing here sun, but because solar system is here, or Earth and ourselves also, we are located in here. Therefore, going back to here, therefore, if the object is moving this one, we don't want to see any blue shift or red shift because there is no change of the velocity on the direction of the side. Why all of the object, when we look through the center of the galaxy, we shouldn't able to see any red shift or blue shift. That is one of the key things that we're going to use on the radio astronomy to our measurement on the next week that we're going to look through it. If we look through the curve in here, it shows exactly what is going on here. It's on this location on the center wave on the 21 centimeter. This is a line of the site that we have. That's a location that is we don't see it on this direction any kind of waves for the 21 centimeter. If, for example, we move it apart from different location, for example, in here, we're looking on different direction, not on the center. When we're looking through here, some of the object is moving here, like this direction, we're gonna see some red shift and blue shift if needed on this direction or on this direction. Therefore, this is the kind of techniques we're gonna use it to see how it looks like. For example, the graph here, if we are 48-degree longitude, we're gonna have this assume here 0, and we have 48-degree, we're rotating in this direction. We're gonna see a little bit 21 centimeter is not happening here. We're gonna have some shift. Originally, when we look through the center, 21 shift is almost located at the exact wavelength that we have here, like here. But here, you're gonna see some shift. Therefore, this is kind of techniques we're using to see the objects. And also same thing, if we go, for example, on this direction, 90-degree, on this direction might be many of the objects have different red shift and blue shift on different direction. And this is the basic of the observation that we're gonna do. And because radio waves is passing through the molecules and the gas and all the material, therefore our measurement for the rotation of the galaxy is more accurate than the visually, because visual we don't see many of the material here. We don't see material here. Many of the area is black and dark, and we cannot observe it on visual. And this radio astronomy gonna help us to measure the things that we needed to have on this object. And this is kind of today we go some basic on the theoretical object of this, how we measure the distances. The scope of this lab is that how we can simply by the radio astronomy measure how much the size of velocity and orientation of the galaxy have. We cannot see it over galaxy like this. This is kind of imaginary picture that we have it here. Only things that we can see it on the radio and also visual observation, just imaginary plane view from the edge of the Milky Way. But by this simple intuition and the Doppler effect, we can easily measure the very good items and the next session that we're gonna go next week on the background and how we're gonna measure the various different things that we're gonna have. And going back to the another things on the next week, we're gonna go to the Skynet, and Skynet, as I mentioned, we have two items. When you go log in on Skynet, you're gonna have optical observation or radio observation. Radio observation, we're gonna see how we can step forward. We go to the new observation. The basic things that we have to learn how to identify this futures, for example, coordinate system. We're gonna go on radio. We're gonna go galactic radio waves. Why? Because we are measuring the based on the galactic coordinate system that we're gonna learn how to identify those on the Skynet and then provide some observation. One key things that I wanna emphasize for you here, you all of you have about 1800 credit. This 1800 credit is kind of can be used for 1800 second observation. And I would like to identify that this, when we're using, we have to use very diligently with this number. And before submitting, you have to double check many things. On the next session, we're gonna go more detail on that, but also in the visual observation. But this is good, about 1800 second, as almost 30 minutes, half an hour time of the observation. If we needed slightly more than that on the course, I can ask from Professor Dan to add more to do that. But I think 1800 half an hour is good enough to do all of the observation, both visual and the radio astronomy. Therefore, this is a kind of top of the hours or first session for the radio astronomy. Any question on the topics that we discussed?
How do you get like more hours or time?
I mean,
How do you get more time on the telescopes?
Become a professional astronomer.
yeah.
Or like this year after you use the 1800?
Well, 1800 is quite a bit of time. We'll see how it kind of goes. I would say a couple things I want to say is for any of you want to swing by my room on Thursday during smart lunch, like B lunch especially, you want to get ahead of the game and try to do an observation. I'll walk you through a little run through how to use Skynet, how to enter some data, and we'll try to do we'll do an optical observation of a planet that you folks will get your feet wet as you get going on this. And overall, if a lot of this seems very complicated, it is, but it gets easier. Like I put in the comments, it does get easier as you go. I mean, the first time I did an observation, it really did take me 20, 25 minutes to go through to get it working. Then I know I was knocking some off in just a matter of minutes, but I would have given really quick. So you learn how to do this. A lot of these concepts the same way. A lot of it's just exposure. And so it takes time, and there's no test every week. So just relax on that. And week by week, you'll just absorb and absorb. Have fun with it as you go in, and always feel like you can come and ask any question. There's no question that's too simple or too complicated. And I won't guarantee that we'll have all the answers either. But if we don't, then we'll try to figure it out too. We'll be just as curious.
Yeah, one of the key items, for example, I give you some idea. For example, if you want to observe the brightest object like a Jupiter or Saturn, as most of them is a second or less than a second. It means that 1 credit you needed for those. But for the very faint object like galaxies that is very faint, might be you needed 20 second or 15 second. It means you needed 20 or 15 credit. But most of the item that you're going to observe on solar system, and also very bright object like um, nebula, Orion Nebula, you're going to have 10, maximum 5 or 10 credit. That is going to provide for you plenty of the pictures during the session, and also same thing on radio. And some part of the OPIS and MWU, we're going to use the archival data. On a Skynet, not only you're going to have your own picture, you're going to have thousands of the picture that taken by the another students or another professional astronomers. Therefore, you can use those as a kind of sample data to do the measurement for your own research. Therefore, this is very good tools that collect all the data as a cloud system in one tool like a Skynet University, and that can be used across the globe. Anybody can have access and use it for their own research. And that's a very plenty of the good tools that you're going to learn on next week's.
Yeah. Yeah. And just echoing that, you really could use this for all types of research in the future. Be very careful. One caution I will have is if you decide to try to do the Skynet on your own, or anytime I submit it to Skynet, at the very end of the process, it will tell you how many points you're using up. And if you get to that last point and it says like it's going to take 100 points, real quick, you're going to back out of that, okay? Or you're going to check. It's okay to check and say, hey, am I doing this right? Because most of what we're doing shouldn't take very many points. And if it does, we'll let you know. So like a boss is saying, most are going to take between 1 and 5 points, maybe 10, maybe 20 if it's a really long exposure. But generally speaking, they're very quick, and we'll learn how the radio works. It might take a few more, a few less. I don't know as we go. But hey, thanks everybody. I know it's an hour already, so we try to stay to that as best we can, respect your time, and to keep this as usable and user friendly as possible. And you know, you folks have a lot of stuff going on. So very glad you're here tonight, and looking forward. I know on Thursday we'll get into Skynet, I believe, on Thursday a little bit, and get a chance to actually take some images together. It'd be kind of fun. So thanks for being here, everybody. Any other questions?
What should we do this week for the lesson?
I would skim ahead through the lessons, kind of look them over in Lab 7. Just you can feel free to look up, and what it does, it'll give you a quick run through of terms and what we're talking about. Because a lot of this takes time to absorb, and you may absorb it very quick. And some of the links that a boss shared and I shared on the side, or if you have time, check them out, and just try to figure it out on your own. We'll go through everything too, but see if you can figure it all out. And then next couple of weeks will go a little quicker, and you'll get a chance to try some of this out.
Yes, as John mentioned on the radio astronomy and visual, we may have on the beginning a little bit slow to get the basics, but when you get the basic, the next weeks gonna be faster and quicker for you and all of us to go one by one.
Yeah.
Any more questions?
Yeah, one more thing. Could you send me the links?
Yeah, I'm gonna after the finish the class, I was gonna send it to you. Just watch out on the email and get back to me, and then hopefully I set up about Skynet and WebAssign for you after the meeting. Just respond back to me on the email when I send it to you, and let me know you have access to check it. Thank you. I hope have a good night, and see you on the Thursday.
Yep. See y'all this week.
Thank you.
Have a great evening.
Have a good day.
Have a good
Bye.
one.
Boss, you want me to stick around a little bit?
Amy?
You want me to stick around a little bit? We can chat.